Mic check. Great. Hi all, and thank you very much for sticking around with me until the bitter end. So yes, as Neil already said, let's talk about Rust. Rust is a very recent programming language designed by Mozilla, and it's kind of claimed to be a safe and modern systems programming language. So let me explain some of these buzzwords here. It's a modern language in the sense that it comes with all the features that we all love from our nice and high-level functional languages, first-class functions like closures, algebraic data types, polymorphism, and traits, which are Rust's take on type classes and associated types. At the same time, it's kind of a low-level language as well, because it gives you control over resource management, in particular memory management. So in Rust, you have control over when memory is allocated and deallocated. There's no mandatory garbage collection. And you also have control over how data is layered out in memory, where there are pointer indirections, and things like that. And Rust ships all of this together in a package with a strong type system that guarantees, or is claimed to guarantee, memory safety as well as thread safety. So in the RustBelt research project, we have, well, essentially, we have the goal of verifying these claims on a mathematical basis. So in this paper, we report on our progress so far. Concretely, the contributions we present here are we defined a lambda Rust, which is a core calculus representing a fragment of the Rust programming language and its type system. We have proven semantic soundness of lambda Rust by giving it a logic relation in iris, which gives us not just a type soundness result, but also a way to reason about unsafe code. And then we've applied this and reasoned about a bunch of the interesting and important unsafe code that comes in Rust's standard library. So before I go into these contributions, however, I will teach you a little Rust. If I only had one slide to explain the type system to you, it would be this one. The central proposition of the Rust type system is to rule out the unrestricted combination of aliasing and mutation. And the mechanism through which Rust achieves this is ownership. So for example, if you create a vector and fill it with some data, and then you call a function, which could be called send, and pass the vector to that function, Rust considers this to be ownership transfer. So you own the vector after you created it, meaning you are the only exclusive person able to access it. And you gave it to send, and now it's theirs and no longer yours. One consequence of that is if you try to do anything to the vector again later, actually Rust will disallow that. It will tell you that v has been moved. And this is actually really useful because one of the things send could do is it could spawn a new thread and put the vector there and have the thread do computation on the side even after send has returned. And then there would be data erase here. And that would not be fun. So in general, if you have some variable x of type t, Rust considers this data to be owned at the given type. Ownership implies that you can do mutation, and hence no aliasing, and you can even deallocate, because really if you own this, nobody else even knows the data even exists. However, ownership can't be everything, because if you look at this example closely, you can see that we actually called a method here on the vector v, and we were allowed to use it again. So what's going on? Well, let's desugar this method call, and then we can see that what actually happens here is that we are creating a reference to the vector and passing that reference to push. So the crucial difference here is that send is passed by a value, which in Rust is interpreted to be ownership transfer, whereas push is passed by a reference, and in this case, push is said to borrow ownership of the vector temporarily. Now, I said temporarily, but I should really make this precise, because we don't want to just be guessing here. How long is temporarily? Well, to control this, Rust uses the concept of a lifetime, which is also called a region in the literature. So in the full type of push, you can see tick A here is the lifetime of the reference which push takes as argument. And it's an angle bracket indicating that the function is actually polymorphic in the concrete lifetime you pick. There is no lifetime given in the source code above, so the compiler infers the lifetime for us. In this case, it infers the lifetime to be just the duration of the function call, which then explains why after the function returned, we can actually call send and use the vector v again, because push can no longer be using it, the borrow has expired. So ampersand mut x is a way to create a mutable reference to some data. Implicitly, there's a lifetime here, which is inferred by the compiler. Mutable references do allow mutation, and hence not allow any aliasing, so mutable references are always unique pointers. Now, we've seen two examples of having mutation and no aliasing, so unsurprisingly, the third example involves aliasing. So concretely, this code creates a local variable, then spawns two threads that both concurrently read a pointer pointing to the stack frame of the main thread, printing the current value of that variable. And then when both threads are done, we mutate x. What's going on here is that %x is a way to create a shared reference with which, like mutable references, come with a lifetime that is inferred by the compiler. And shared references, as the name indicates, they can be aliased. They can be shared by multiple threads in this case, and hence they do not allow mutation. We can also see that in this case, the lifetime inferred by the compiler is actually the duration of this join function call, which means that once join is done, and both threads are actually done computing, we can mutate the variable again. So shared references having a lifetime means that we can temporarily make data read-only and shared, and then later regain full exclusive access. So to summarize what we've seen so far, Rust's type system is based on ownership, which comes in 3 flavors. There's full ownership, you can do anything you want. And then there's 2 kind of temporarily borrowing ownership, which comes in the flavors of mutable and aliasable. And both of these are controlled by lifetimes. So this is all working very nicely. The problem now is this seems pretty restrictive, right? Sometimes you do need alias mutable state. Maybe you're doing shared memory concurrency and you have logs or something like that. Maybe you prefer message passing and you have some channels that send data between threads. There's also shared mutable state there. Or maybe it's a sequential setting and you're doing reference counting for your memory management. So what is Rust's answer to this problem? Well, let us look at an example. This program creates a mutex, and mutexes contain data in Rust. So we initialize this with the value 0. And then we spawn 2 threads that both acquire the log, do some error handling, or rather not do error handling, ignore the unwrap here, and then increment the value that's stored in the log, and implicitly the log is then released again when this goes out of scope. And then once both of the threads are done, we print the current value, and of course we expect this to be 3. So to understand what's going on here, we should look at closer at the type of this log method. First of all, it's a polymorphic method, again, working on any lifetime. And it takes a shared reference to a mutex as its argument. It's crucial that this is shared because the whole idea of a log is that multiple threads can be racing and trying to access the log at the same time. So if we wouldn't allow aliasing here, that would not make any sense. The return type is a little unwieldy, but you can essentially think of this as being a mutable reference. There's some more magic going on to do this automatic unlocking. So what we're seeing here is a method which takes a shared reference and then gives you a way to mutate stuff in there. This is a phenomenon that has several instances in the standard library. It's called interior mutability. And it seems to completely break everything I said so far. And it seems to be also inherently unimplementable because the Rust type system shouldn't allow you to do anything like that. Well, for the second part, the reason this works is that Rust has unsafe blocks. And inside unsafe blocks, there's additional things you can do, and the compiler kind of says you're on your own there. So for example, you can call into the operating system and ask pthread to please acquire a log for you. And this is what the implementation of log does if you run it on Linux. However, the claim of the developers of this library is that even though the implementation of the mutex is unsafe, its API is safe. So if you write safe code that uses the mutex, you can't screw up, and you can't have data races or other kind of memory problems. And this is not isolated to mutex. The expressivity of Rust is continuously extended in this way, not just by the standard library, also by user libraries. So this join method we've seen a couple times is actually an additional library that you can add into your Rust code, which has a sophisticated implementation based on a work-stealing thread pool, also using some unsafe code to be, well, possible and also to be efficient. And again, the claim of the author is if you use this from safe code, your program is not going to crash or have any other kind of memory or thread safety issues. So this brings us back to the goal of our RustBelt research project. We want to actually prove these claims of the Rust type system developers and of the library developers true. And clearly, because of this extensible nature of Rust, we have to do this in a way that our proof is also extensible, and we can kind of prove new unsafe libraries safe without redoing the entire proof. So now in the second part, I'm going to give you an impression of what we did there. We defined this lambda Rust language and a type system for it. The type system comes with a bunch of built-in types like booleans and integers, 3 kinds of pointers matching the 3 kinds of ownership that Rust has, owned pointers, mutable and shared references, sum types, product types, and also, of course, function types, recursive types, all the usual business. These types are then collected in a typing context, which assigns types to paths that provides a way to directly talk about the types of individual fields of structs, because the Rust type checker actually tracks these separately for the purposes of these references and borrowing. And of course, we have a couple typing judgments, which are substructural. Shouldn't be a surprise. After all, the Rust type system has ownership, and you can lose access to data. So we have a typing judgment for typing individual instructions, which, as usual in substructural type systems, comes with a pre- and a post-typing context, indicating which stuff you have before and after executing the instruction. And there's some additional context for tracking lifetimes. And then we have typing, typing judgment for whole functions. And whole functions are written in continuation parsing style, so it doesn't come with a post-typing context. Instead, it comes with a context K, tracking the possible continuations. So, of course, you may not be expecting me to show you some typing rules. So we do have typing rules. We have plenty of typing rules. In fact, we have so many typing rules, I'm not going to show you any of them, and focus on the high-level aspects of the type system instead. The usual thing we would do now is prove a form of syntactic type safety result through progress and preservation. But the problem with this is we then would not have a story for doing unsafe code. So we do essentially what Derek told us to do in his keynote, and we use a semantic approach based on logical relations. Concretely, we define an ownership predicate. You can think of this as a somewhat elaborate version of this value relation that Derek had in his talk, that for every type, tau tells us what does it mean to own data at this type. Ownership predicates in our model take two arguments. One is the thread ID of the owning thread. Rust has a notion of types being thread safe. And so we make ownership kind of depend on the thread to be able to model that. And the second is a list of values. It's a list because Rust types can describe data in memory. So we can kind of think of this as being all the adjacent memory sets, one after the other, and then the predicate tells you, is this valid at the given time? Once we have defined this for all types, and we'll later give you a glimpse for how we do that, we can, So of course, we define this predicate in Iris. Shouldn't be too surprising. And that's very useful because Iris kind of comes with the built-in notion of ownership. So we don't have any trouble modeling that part of Rust. It's also useful because Iris lets us derive new reasoning principles inside the logic, and this will be very useful later. Once we've defined this ownership predicate, we can lift it to contexts, and you can see already here that we are fully using the fact that we are in a separation logic. Clearly in Rust, if you have two vectors and give away one of them, you want to know you still have the other vector. So we put a separating conjunction between the elements of our typing context. And if we wouldn't use the separation logic, we would now have to start manually talking about splitting resources. We don't want to do that. Once we have all the typing contexts defined, we can define typing judgments. And again, we make use of the fact that Iris provides a program logic. So we use a Hort-tripper to say what does it mean to be a well-typed instruction, where the pre and post typing contexts become pre and post conditions of the Hort-tripper. So next, we have to show that our semantic triples have anything to do with the syntactic type system we defined previously. So here are two of the typing rules I didn't show you. And the exact rules don't matter. The important thing is there's a bunch of turnstiles there, single turnstiles. And what we now do is we replace them by double turnstiles. And this makes it a statement in Iris. And for every single proof rule, we go ahead and prove this Iris statement as a theorem. Once we did all that, we get as a corollary that well-typed programs can go wrong. So there's no data races, and there's no invalid memory access. However, we actually get much more than that. If we have a large program, which is mostly written in safe code, but then uses some unsafe library, let's say mutex, then, well, we can type check the safe part of the program, and we get a typing judgment for that, but we can't type check mutex. It uses features which we won't get a safe type system for. However, we can manually prove that mutex is semantically well-typed at the type that it is given in its API. And because we have shown that every single type, that we have shown these compatibility lemmas for every single typing rule, we can actually lift the semantic soundness of mutex and link it with the syntactically type-check code and obtain semantic soundness of the entire program. So in other words, the whole program is safe if the unsafe pieces are safe. And this is where the semantic approach really gives us a much stronger result than just showing a syntactic type safety result. So in the last part of the talk, I want to give you a brief impression of how this type ownership predicate looks like. So let's have a look at owned pointers to some type tau. There's a bunch of bookkeeping going on here because we have these lists. But what this means, what it says at its core is hopefully the kind of interpretation you would expect. There's a maps to there saying we own some memory behind some location L. There's a list of values W, and this list of values is a valid tau, whatever the pointer points to. Right? Now, the really interesting types, of course, are the ones which make Rust kind of different. There are these reference types that come with a lifetime, right? So first of all, I would like to point out how the mutable reference is pretty similar to the owned pointer. It also has this maps to some list of values, and then there's the list of values is valid at tau. But then there's this funny thing here, which is this looks like a type, but it's actually a connective in the logic. It's like a modality. We find a way to be able to talk about borrowing in separation logic in general, not just syntactically as part of the type system, and we call this the lifetime logic. The central proposition of the lifetime logic is that in contrast to traditional separation logic, where you split ownership in space, right? P star Q means P and Q hold for different parts of the heap. In the lifetime logic, we can split ownership in time. So let me demonstrate this by looking a little closer at the central proof rule of the lifetime logic. At the bottom, you can find a timeline where now is the point in time when the rule is applied. And dagger kappa is the point in time when the lifetime gets killed and ends. So before dagger kappa, kappa is alive. After dagger kappa, kappa is dead. Now, this rule says that if we own any assertion P, then we can do the following. We can split P into two parts, where the first part grants us access to P while the lifetime kappa lasts. That's from now until dagger kappa. And the second part grants us access to P when after kappa has ended. So that's essentially from dagger kappa until the end of time. And because these two parts of the timeline are disjoint, it is justified to put a separating conjunction between these two pieces, even though they both talk about the same resources P. And the way we've shown that this makes any sense is we have given a model to the lifetime logic in Iris and proven correct its roots. And this is where we've really fully homed in on Iris's ability to be able to derive new reasoning principles inside the logic. We didn't have to touch the model of Iris to be able to do the verification. So this brings me essentially to the end of my talk. In the paper, we show a couple more details about lambda Rust, the language, about the type system, some of the typing rules I didn't show you, and of course the lifetime logic and a whole bunch of rules for that. We also show how we can handle interior mutability. Remember, that's this idea where you can actually, in controlled ways, mutate shared data. I hope it's somewhat intuitively clear that this makes the justification for why shared references work more complicated, right? It's not just shared references are read-only. In a mutex, you can actually write to them. So the justification can become more complicated. We explain how that works and for two concrete types, mutex and cell. Moreover, we have a Coq formalization where we've shown a couple more types that also all involve interior mutability to be semantically well-typed. And in one of them, we actually found a bug that we've then also fixed in the Rust library. That said, we don't model full Rust. There are still a couple of things from in Rust that we didn't handle. One of them is trait objects, which are essentially a form of existential types in Rust. We don't handle weak memory, so we consider things to be sequentially consistent, but we do have a notion of non-atomic accesses so that we can reason about data races. And we don't consider drop, which is kind of Rust's automatic destructor. And there have actually been some interesting issues there as well. So this is certainly very interesting future work to look at. So to finish up, we claim that logical relations are a great way to prove safety of languages with unsafe operations. And in this paper, we have shown that advances in separation logic, as realized in Iris, actually make this possible for logic that is as sophisticated as Rust. Thank you.
Excellent. So is the way to think about this that the only unsafe actions modeled here are ignoring the ownership protocol, or are there other kinds of unsafety, like, for example, an unsafe coerce operation?
Unsafety allows you to do anything. You essentially drop down to C. You have full casts, raw pointers, pointer arithmetic, everything you can do in C.
Oh, wait, how much of that is modeled in here, though?
We don't model all of the subtle cases of undefined behavior, but certainly our language does allow you to do adverse arithmetic and deallocate stuff too early and still try to access it and all of that. So we have our language is a low-level language with deallocation and pointer arithmetic and everything. And we prove that you don't access data that has already been deallocated or that is out of bounds.
I see. Thank you.
So first, thanks for the talk. So it's kind of, you have explained that if you had two mutable references and you would send them two different threads and both threads that mutate them, obviously that would pose a problem. And that's why you said multiple references are not allowed, multiple of them. So now the question is, from my experience from using Rust, like in most of the cases, of course, most of your variables and data structures you don't send to other threads. Still, you cannot use multiple mutable references. And now the question that I kind of sometimes had is this a restriction that has some kind of background, so that would something break down except for the threading part if you were to use multiple mutable or if it were allowed to use multiple mutable references, or is this just because it's considered not a good style to have multiple mutable references?
Things would break. One example is iterator invalidation. If you have a mutable reference or any kind of reference into a vector, but then also have a mutable reference to the vector as a whole and like empty it, now your inner reference is broken. So this completely solves iterator invalidation in a static way. Another example is Rust has sum types. So you can actually change the type of memory by switching. Sometimes they're implemented as unions, overlapping memory. So you can change the type of a particular location in memory by switching to a different variant. So if you would have still a mutable reference into the thing and then mutate the outer thing, now your inner reference is at the wrong type.
Okay,
so even in sequential code, you have the same problems.
That's kind of what I wanted to hear.
Very nice talk. I had a couple of questions. One is I was pretty intrigued by your lifetime separation concept in your paper. And it reminded me of cryptographic storage protocols where you have revocation of keys owned by a owner, so they can define different access controls for different points in time. So have you considered kind of using the theory developed in Iris to kind of look at verification of those storage protocols?
Not yet.
Okay, but that seems like a promising direction.
Yes.
Second question was kind of related to the previous question, which is you mentioned that there are lots of uses of unsafe in Rust, and some of them are for optimization. So did you discover during this project some reasoning principles that you can translate back into type system concepts to kind of enrich the type system to not have to use, to kind of take those unsafe uses and transform them to safe uses?
Not really. We've mostly been focusing on looking and kind of proving the existing thing. That said, our type system is more flexible than the actual. So we can type check more programs than Rust can. Maybe not strictly more because we don't have a formal version of what the compiler concretely does. But there's certainly programs we can type check after manual translation into our core calculus, which the Rust compiler doesn't type check. That said, the Rust compiler is currently being extended with a new lifetime mechanism, non-lexical lifetimes, which is extremely powerful and seems to, in some places, be even more powerful than what we model. So there's certainly going to be a little bit of back and forth there in terms of adjusting the power of what we can prove and what the Rust compiler is able to check.
Okay, thank you.
You said that you had verified the mutex code as being safe. Does that mean that you have a formal semantics for p-threads?
No, we've modeled mutex by doing a spin lock.
By
doing a spin lock.
Okay.
So we've not focused on the actual C implementation. It was more is code of this behavior, which after doing mutual exclusion gives you a Rust like type level mutable reference. Is that actually a sane and safe thing to do in Rust? And that's what we've proven.
Okay, we got time for one more question if anyone wants to ask something. Okay, then I'll take the opportunity to ask a question. So often one of the advertised benefits of linear types is that it guarantees the allocation of memory. Can you prove anything similar for Rust?
No, Rust type system doesn't guarantee. The question is linear type systems often guarantee that you don't have leaks. Rust type system doesn't guarantee that. Essentially, they made this choice deliberately because they tried to find a way to have ref-counted pointers and still guarantee leak freedom and didn't find anything that was sane, and then decided that they don't guarantee that. So the core Rust without any unsafe code you could probably prove a theorem like that. But Rust, as it used de facto with the standard library, does not guarantee leak freedom. And anyway, Iris is not currently set up to prove leak freedom, so we couldn't prove that anyway.